All right, well, hello, welcome. I was going to try to attempt to stream this, but for one reason or another, I can't get the bandwidth that I need to get this to go live on the YouTube channel. So I'll dig into that and see what's going on there. Could be a bandwidth issue or otherwise. But anyway, what I wanted to do was go through a couple of the mastery examples, and that way you can kind of check over your mastery worksheet. Again, this is just whenever you have a chance over the 3-week period that we're away. It sounds more and more like we might end up being put in a distance learning situation. And so it'll be important that you're able to get on Classroom and, of course, access these videos that I'll be posting. And if I can do live sessions, I'll try to. Maybe even doing live sessions through Twitch. Kind of depends on how the bandwidth and how I'm able to actually get things out there in a live format. So without further ado, let's go ahead and get started on a couple of them. All right, so the first one I want to do together would be CH3I. All right, so we should first go ahead and tally up the valence electrons, right? So we're going to get 4 from carbon. We're going to get 3 total from the hydrogens and 7 from iodine. We add those guys up. That's a total of 14 valence electrons. Central atom. Carbon's in here, so we should usually go after carbon first. So we'll put that guy in the middle. And we're going to single bond to each of the other atoms in our molecule. So I'll just put the hydrogens at the bottom, left, and top. There's really no reason for that, but personal preference, right? And then iodine can go on the right-hand side here. We now have used 8 electrons to do this. There's 6 left over. The 6 that remain will need to be placed around atoms that require an octet. First, we look at the terminal atoms, and we know hydrogen is okay with just 1 bond apiece. And then this iodine definitely could use some valence electrons, so we'll give it the 1, 2, 3, 4, 5, and 6. That gives it the octet set of electrons, including the shared pair, and this looks pretty good. We've used up all of our electrons, and so we can evaluate formal charges, but again, everything's going to have a 0 formal charge because hydrogen arrives with 1 and is assigned 1, carbon 4 and assigned 4, iodine 7 and has been assigned 7. So this looks good. What we need to do next is look up electronegativity values, and this will allow us to determine whether or not these bonds are polar and just how polar they might be. So hydrogen, we look it up and it's 2.20, so we'll mark that in for each of them. All right, carbon is 2.55, and iodine is 2.66. There we go. So let's go ahead and draw in our dipole arrows on these. All right, and I'll use a green arrow for that. So between carbon and hydrogen along this bond, the electrons would prefer to spend more time on the carbon because it has a higher electronegativity. And then between the carbon and the iodine is slightly more electronegative. Now, so this bond here would fit underneath our category of largely nonpolar covalent. However, there is a difference between these EN values, and so I instruct you guys still to put the arrow pointing towards the higher electronegativity atom. All right, now before we decide what's going to happen with this entire molecule, whether it's polar or not, we also should probably evaluate the geometries, and as well as sketch in the 3-dimensional Lewis structure for this. But just before we get there, let's go ahead and make sure that we do shade in or mark in the lower EN values will be kind of highlighted in red. So we'll kind of do that, color over these hydrogens in red. And then the highest electronegativity value, we will mark in blue. So let's go ahead and color over that in blue. And anything in the middle, I'm just going to leave alone. And what that helps me do is kind of see how the electronegativities are laid out in the molecule. All right, now as to that geometry, we can recognize that this is an AX4 E0 or axis notation. So we can mark that in here, AX4 E0. That means its domain geometry is tetrahedral. And as far as its molecular geometry, an AX4E0 is still going to have the same EDG as it does in Mg, so this will also be tetrahedral. Now, to get its three-dimensional look, we don't need to put lone pair electrons on terminal atoms, but we do need to use like dots and wedges and solid lines to represent bond lines that are like in the same plane or coming towards us or going away from us. So I'm actually going to, I think, put my hydrogens at the bottom of this. So I'm going to put one hydrogen down here and to the right. I'm going to put the iodine in the same plane as that hydrogen atom. And then the other two that are remaining, one will come down and towards me off the paper. One will go deeper into the paper, into the background. And then if it also helps, you can draw the same dipole arrows on your three-dimensional structure, right? So we can still draw that these go, up towards the carbon, up towards the carbon, up towards the carbon, and then from the carbon up towards the iodine. So I think the three-dimensional structure helps us kind of see that there's definitely going to be a preferred end to this molecule, like where electrons want to spend more of their time. So evaluating this, we notice that the dipole arrows do not cancel each other out. We also notice that we have an asymmetric atomic bonding arrangement here, where we don't have hydrogen at each of these 4 bond locations. If we did, then we would have the 2 criteria met for nonpolar molecules, where we have a symmetrical geometry and we have atomic symmetry, with every single atom bonded at the terminal ends being the same. But we don't meet that criteria. So this is definitely a polar molecule. And because it is polar, we're going to go ahead and shade in, or we can bubble around the region that will be, this will be our partial negative region. And the hydrogen end, we'll bubble that around, and that will be our partial positive side. So this is our shading then for a molecule. You can also do the shading on the three-dimensional structure. If you decide to do it over here, maybe it's easier for you to do it that way, and that's fine too. Again, partial positive by the hydrogen and a partial negative charge nearest the iodine. So, like, how polar is this molecule? Well, we know that we have a 0.35 difference between the hydrogen and the carbon. So that's going to be a slightly more polar bond than what we see between the carbon and the iodine. However, again, we still have this overall pull towards the iodine. So this will be, this would be a polar molecule, but it may not be like, massively polar, like compared to, say, like a water molecule. All right. So that's number 4. Let's go ahead and let's hop to number 6. All right, so I apologize for the font that I used here. I used Arial font, and I use Arial font a lot, or the Calibri font as well. And that being said, lowercase L's sometimes look like uppercase I's. And so this is ClF3, right? Not CIF3. All right. So let's go ahead and do electron count. 4 from the carbon, or sorry, geez, I just got myself on that too. All right, so for chlorine, 7 for the chlorine, right, plus 21 from the fluorines, all right, so a total of 28 electrons to deal with. All right, so let's go ahead and put Cl at the middle. Why Cl go in the middle? Because it has the lowest electronegativity value compared to fluorine. Well then, let's go ahead and we'll put these in like a trigonal planar format. I don't know if that's how this will play out, but we'll go ahead and do that anyway. And then let's see, we need to remove the electrons we've used so far. So -6 from bonding, that's 22 left. We're going to place 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6 dots around each of these fluorines to give them the octet that they need. That uses 18 electrons, which there are 4 that remain. Those 4 will go onto the central atom. So we'll put a lone pair there, and let's put a lone pair down here. Okay. Now, I'm going to go ahead and put the lone pair bubble around these so I remember or recognize that these are lone pair electrons and they're on the central atom. All right, electronegativity values. let's see. Oh, why don't we check formal charges just to make sure that we had this correct, right? So chlorine should have 7, and we have assigned it 1, 2, 3, 4, 5, 6, 7. So chlorine has a formal charge of 0, and fluorine also has a formal charge of 0, being assigned 7 and having a 7 valence already before it bonds. So this is the best structure we can come up with. Electronegativity values, fluorine is 3.98, so it's very electronegative. 3.98 and 3.98. Chlorine is 3.16. So our dipole arrows, no surprise here, will point out towards each of the fluorines. All right. Now, before we start jumping to conclusions about whether it's polar or not, let's go ahead and mark in the fact that chlorine is going to be the lower end atom, and fluorine will be the higher EN atom. So we'll go ahead and give it the blue marking here. All right, and let's determine its geometry. All right, this is going to be an AX3 E2 axial notation, which means it's 5-domained. So this is going to be, yep, you guessed it, trigonal bipyramidal. And for its molecular geometry, because it has some lone pairs, that's actually going to change some things for us. Remember, in a 5-domain molecule, the lone pairs are placed around the equator of the molecule. All right, so in an AX3E2, we would actually have 2 lone pairs placed around the equator. So if you recall from your Vesper chart, this guy is going to be T-shaped. But let's go ahead and draw it in a 3-dimensional format, and that might help us understand that. So first, we'll put our central atom in here, the chlorine. And then we're going to recognize that we need to place a couple of these fluorines at the north-south pole. Then we're going to place our 3rd fluorine on the equator, and then these 2 lone pairs are going to take up the other 2 spots on that equator. Right? So these guys right here are like around the equator of the molecule. They're kind of coplanar. And so the remaining shape that we have here is going to be a T-shaped molecule. So let's go ahead and draw in our dipoles onto the 3-dimensional structure. We're going to have pole to the north and to the south, fluorine, but we'll also have this pole out towards this right-placed fluorine. So we do not cancel these dipole arrows, and therefore the molecule would be polar. And I think it'll probably be easiest if I use the 3-dimensional structure to kind of show where that will happen. Around the fluorines, we're going to have that partial negative charge. And then on the chlorine side, we're going to have that partial positive half or end to the molecule. Right, but I could also have tried to do it here, but I'd be really reaching, I think, around with that blue cloud here. So partial negative. And then over here would be our partial positive. I think it's easier to see what's going on with the 3-dimensional drawing. Okay, let's move to number 8. Number 8, we got BRF5, so bromine pentafluoride. We're going to get 7 valence from the bromine, plus, 35 from the fluorines altogether. That would be 42 total electrons. Central atom should be the lowest with in electronegativity. That's going to be the bromine. So we'll put bromine in the middle. And again, not really sure how this might play out. We definitely have 5 bonded atoms here to deal with, so we'll go ahead and do that. So we'll do like 1, 2, 3, 4, and 5. We'll put our fluorines at each of those bonds. To do this, we used 10 electrons to do that because we have 5 bond lines going on. That leaves 32 electrons left. From these 32 electrons, we're going to octet each of these. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. We have used 30 electrons to do that. There are 2 that remain, and those have to go to central atoms. So we'll put a lone pair bubble on there. And let's determine electronegativities. We know that fluorine will probably be the most electronegative with 3.98. Bromine will be 2.96. So we know that the dipole arrows are going to point out to the fluorines. So from bromine to fluorine, bromine to fluorine, bromine to fluorine, and so forth. All right. We also know that that means that the fluorines will be our blue shaded atoms because they have the highest electronegativity, so they will be electron hungry. And the bromine will be the lower of them, so we'll shade him in red. The geometry. This is going to be an AX5E1. That's a 6-domain molecule, which means this guy is overall octahedral. And in a 6-domain molecule, the lone pairs are actually placed on the north or south pole of the molecule. So this one will actually be, for its molecular geometry, a square pyramidal. Or square pyramid, either way is fine. Let's go ahead and do its 3-dimensional sketch. For this one, out of convenience, I think it would be best just to go like bromine here in the middle. We're going to do a fluorine to the north pole. We're going to do the remaining ones. There'll be a dotted line that goes back to this fluorine, a dotted line that goes back to this fluorine. We'll then do 2 wedges here. And that's will be where the other fluorines reside. And at the bottom, on the south pole, will be the lone pair that we have here on bromine. And again, if it helps, you can draw the dipole arrows. These 4 fluorines are all coplanar, so they actually cancel each other out because what goes back into the right is also taken care of to forward and the left and so forth, because they're all these are all in the same plane. They're in the same around the equator of this molecule. But it's this one here at the top, the draw towards that top fluorine, that's going to really set it up as being a polar molecule. So again, I think the 3-dimensional structure might be easier to go with, but of course, the way I've drawn the 2D sketch, it also would work where we can show that around this north pole fluorine, there is a partial negative charge, and around the bromine, that's where we would have the partial positive charge. So either way you want to show that is fine. If you have color pencils or whatever, you can just lightly shade that half of the molecule and lightly shade the other half, the red. All right, so there you go. There's BRF5. All right, let's keep moving. Let's hop to number 12 and number 13. I believe these are the last 2 that I have on the agenda to do today. Yep. All right, so first things first, total electron count. We will get 6 from the sulfur, right, plus 28 total from the fluorines. That's going to be 34 valence electrons. Sulfur will go in the middle. We'll then single bond to each of the fluorines. And that's 8 electrons there. That leaves us with, 26 electrons left. We'll then go ahead and octet the terminal atoms with 6 electrons added to each of these fluorines. So to do that, that's 24 electrons. That leaves 2 left over. Those 2 will go to, yep, you guessed it, central atom. We'll put like a little lone pair bubble around that. As far as electronegativity values go, fluorine is always 3.98. And sulfur is 2.58. So there's definitely a difference there, a significant one at that, and these dipole arrows will point out to the fluorines. All right, let's see. We should also do our color coding for our atoms. Fluorine, again, we'll get the blue shading around it because it is the higher electronegative atom here. And sulfur, with its lower EN value, will get kind of shaded in red. Before we get too crazy about polar or nonpolar, we should do our geometries again. Axion notation, this will be an AX4E1 axion notation. This would be 5 domains, so its electron domain geometry would be trigonal bipyramidal. There we go. And for the molecule itself, remember that in a 5-domain molecule, the lone pairs will be found around the equator of that molecule. So this will actually be the seesaw shape with, let's go ahead and put, in our 3-dimensional sketch, we'll put sulfur here. And then our north and south pole fluorines. And then we're going to put a lone pair over here, and we would have a fluorine that comes towards us off the page and a fluorine that goes away from us into the page. All right, so again, just kind of noting that, you know, this part of the molecule is equatorial or coplanar. They're all on the equator there. Again, I don't think it matters which drawing you want to use for your color code or your cloud for polarity, but this is a polar molecule, and it's going to be the side or edges with the fluorine that are going to be the negative region of this molecule. So we can kind of put a cloud around that and put a partial negative region there. And the positive region would be around the sulfur. We could also show that in the 3-dimensional sketch, if it's a little bit easier to do that, where this part here would be your partial negative charge. And this part over here would be your partial positive charge. All right, so hopefully that worked out well and we match up with that. Last one that I wanted to go over with you guys would be CH2Br2. All right, so this one I think is a lot more straightforward and easier to do than some of the other ones we've done today, but I still think it's probably going to be helpful to do it anyway. All right, so we're going to have 4 electrons from carbon plus 2 from each of the hydrogens, combined anyway, and then 14 total from the bromines. So that's a total of 20 electrons to deal with. Central atom, if carbon is present, we usually put that in the middle. So we'll go carbon in the middle. We'll do a single bond to the hydrogens. We'll do a single bond to each of these bromines. And to do that, we have used 8 electrons. We are at 12 remaining, and we will use those 12 to give bromine the octet that it needs. All right, so it looks to be the appropriate Lewis structure. Let's go ahead and get EN values assigned. For hydrogen, it's 2.20. For carbon, it's going to be 2.55. And for bromine, it'll be 2.96. All right. We can do some color coding, I suppose, here. The highest EN valued atom would be shaded in blue, so we'll shade these bromines in blue. I really need to get a new blue marker, don't I? And the hydrogens would be the lowest here. So we'll mark those in red. Okay, dipole arrows. We're going to point from the hydrogen to the carbon, and then from the carbon to the bromine. All right, so before we decide on polarity, let's go ahead and do our geometry. This is going to be an AX4E0 Xe notation. That puts it in a tetrahedral geometry. And because we have 0 lone pairs, it also means that the molecular geometry is also tetrahedral. Let's go ahead and do the three-dimensional Lewis structure while we're over here. Carbon in the middle. We'll put, I don't know, we'll put hydrogen in the same plane. And then we'll have one bromine coming towards us. And another bromine going away from us. Again, if it helps to draw the dipole arrows on the three-dimensional sketch, go ahead and do that. Whoa. There we go. Should go from hydrogen to carbon. There we go. All right, so we can tell that the dipole arrows do not cancel out. They actually have a flow to them. They want to kind of head towards from hydrogen to carbon, then from carbon to bromine. And that would indicate to you that this molecule is in fact polar. The difference between the EN values is not very large from hydrogen to carbon, but it's a little bit larger from carbon to bromine. This one would be definitely a polar molecule, though, with a negative region found around the bromines. So this would be a partial negative region and a partial positive around the hydrogens. All right, so this is a polar molecule for sure. So again, just kind of check your work over. If these match up with what you've come up with, then that's great. You're in good shape when it comes to Lewis structures, geometries, electronegativity values, and then assessing the molecule if it's overall polar or nonpolar. And so if you have any questions, feel free to bounce ideas through email or whatnot, and I'll probably be posting something within the next couple of weeks just to kind of check in and see how we're doing.